The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, I'm going to talk about 3J, 6J, and wigner-eckart theorem. This is a topic that I've always not liked using 3Js and 6Js because I felt that for most of the problems that I wanted to work on, I could derive all of the angular momentum transformations using raising and lowering operators and orthogonality and doing some very elaborate algebra. And for some reason, I thought that that was virtuous and wonderful, and I didn't want to have to refer to these transformations. They are very convenient, especially now that you can ask computers to do almost everything that I once did by hand. And so let's talk about transformations between basis sets and what are you going to do with these transformations between basis sets. So as an example, I'm going to use one problem that I've used many, many times before, and that's the Spinorbit and Zeeman Hamiltonians for atoms. And for atoms, we always we encounter two different basis sets. We encounter the coupled basis set and the uncoupled basis set. And so the coupled basis set is L, S, J, Mj. And the uncoupled is L, Ml, S, Ms. And these two basis sets have labels here. This corresponds to an eigenvalue of L squared, of S squared, of J squared, of Jz. And so these are the quantum numbers we use to specify the basis functions. One of the useful things about this is that whenever an operator is applied to one of these things, if it's for this one, if it's L squared, S squared, J squared, or Jz, we know what happens. And even if it's J plus minus, we know what happens. And so when we have operators like this, we think, well, I probably ought to use this basis set. Similarly, we have a set of operators for this basis set that we're comfortable with. But suppose I were to ask you, well, what does J plus do to this? And you would say, well, I don't know. I have to do something. I have to do some work. And and what does L plus? So I guess I wrote, no, I didn't. What does L plus do to this? Again. All right, so let's now look at a semi-real problem and discover the need for transformations between these two basis sets. So let's look at my favorite Hamiltonian, the Spinorbit Hamiltonian, and let's just use the simplified form of the Spinorbit Hamiltonian. There are people out there looking in the window wondering what kind of a crazy person this is. But they left. So the Spinorbit Hamiltonian in the simplified form, the one that operates within a particular value of L and a particular value of S, which is a reduced form, but it's useful. And even with that reduced form, one gets into trouble. So we have a constant, which is zeta NLS. The different value of the constant Well, n is just the label of what is the electronic configuration, and we get a different value of this constant for each value, a combination of L and S. And so, and the action all comes from this L dot S operator, and we can write that as LZ SE plus 1/2 L plus S minus plus L minus S plus. Okay, no big deal. And we can write the Hamiltonian, the spin-orbit operator like this. Why do I write these commuters? Oh yes, okay. We know that the Hamiltonian, the spin-orbit Hamiltonian, commutes with J squared. We know this because, well, we know this for several reasons. One is L is a vector with respect to J. S is a vector with respect to J. Dot product of two vectors with respect to J is a scalar. So we know that this thing is scalar with respect to S squared. It's going to commute. Another property of scalars is that it's going to commute with JZ as well. This thing, though, if we ask, well, what is this with respect to L squared? Or what? The spin-orbit Hamiltonian is not a scalar with respect to L, because this is a vector with respect to L, and this is a scalar with respect to L, and so this is a vector. So we can't write this is not 0, and all of the components of J here, all the components. So it's telling you that the coupled basis is a good basis for dealing with spin orbit, because you're guaranteed to get diagonal matrix elements. The uncoupled basis is probably a bad idea for dealing with the spin orbit Hamiltonian. So if it's a good idea, then there ought to be a way of rewriting the spin orbit Hamiltonian so that we see immediately that we get diagonal matrix elements in the coupled basis. And this is a trick that is used almost always when you have two angular momenta coupled to make a third. The coupled basis is always a good basis, and most operators that you're going to encounter are dot products between two angular momenta. And so you always want to choose a basis set that makes that dot product really trivial, and this is the way it's done. So we have L is equal to J, J is equal to L plus S. These are now not numbers, but operators. And so J squared is L squared plus S squared plus 2 L dot S. And so we can always arrange this as L dot S is equal to 1/2 J squared minus L squared minus S squared. So here is an operator that we'd like to look at, determine the matrix elements of in some basis set. And here are three operators. And these are three operators which are diagonal in the coupled basis and not in the uncoupled basis. We have trouble with this in the uncoupled basis. These two are just fine, but this is not fine. So we can evaluate matrix element of the spin orbit Hamiltonian in the coupled basis by taking this trick And we get that LS, J, MJ, spin orbit, LS, J, MJ is going to be equal to zeta over 2 times JJ plus 1 minus LL plus 1 minus SS plus 1. And we could put little things up here, and then we'd have 4 Kronecker deltas. This is exclusively a diagonal matrix element. And you write it in terms of really trivial stuff. And you think, well, am I just lucky? Is this a trick that somebody has to be really clever to pull out of their back pocket? Or is it a trick that whenever you have a dot product between 2 angular momenta, it's always possible to choose a basis set that makes evaluation of those matrix elements trivial? And that's the answer. However, sometimes you have a problem because you have another operator that you have to deal with, like the Zeeman Hamiltonian. The Zeeman Hamiltonian is the Bohr magneton times LZ plus, for chemists it's 2, for physicists it's not quite 2, BZ. So here's an operator. I should also mention the Hamiltonian is always a scalar. The Hamiltonian for in the presence of a field is never a scalar. Okay, so here we have operators, and you look at this and you say, well, I'm going to use the uncoupled basis set. Well, but you want to use the coupled basis set for spin orbit. What would happen if I tried to use the coupled basis set for Zeeman? Well, you don't know what LZ or any component of L does to this thing. So one solution is to say, well, I guess I can't use the coupled basis set. Well, if you use the uncoupled basis set, then spin orbit is massively off diagonal, but all the matrix elements are trivial. And you could live that way. But when you have a matrix which is exclusively diagonal, and there's one other thing that you need, or 2 other things that you need that are, and you could even say, well, LZ is equal to JZ minus SZ. And so really, and you know what JZ does in the coupled basis. So there's really only one thing you don't need, that you need to know about. So you need to know LZ on this or SZ on this. And so what do? Well, one way to solve this is to say, I'm going to write a transformation between the coupled and uncoupled basis sets. So let's do that. So here's a coupled basis function. And to write a transformation between basis sets, you use completeness. And so you want to end up with L, ML, S, MS. And so to do that, you have L, ML, S, MS. This is completeness. We have to sum over something. And this is the original L, S, J, MJ. Okay, I don't need 2 bars. So this is completeness, and this is a transformation coefficient. This is something we want. Okay, and now in doing this transformation, we have L and S, but we we've lost j, and we haven't lost m sub j because we have m sub l and m sub s, which are the same thing as m sub j. So we're going to do a transformation that trades m sub j for either m sub l or m sub s. And so we're going to do a sum over so we're going to do a sum here, which is a sum over, let's say, m sub s, and it goes from minus s to plus s. And we can rewrite m sub l as m sub j minus m sub s. And so we're just doing the sum. And this would be in the case that L is greater than or equal to S. If S is greater than L, well then we would sum over M sub L from minus L to plus L. So we can formally write a transformation either in the forward direction, going from coupled to coupled to uncoupled, or from uncoupled to coupled. Now, these are angular momenta. We define angular momenta. That was an involuntary rather than a voluntary remark. Okay, so we have angular momenta that are defined by I h bar sum over k epsilon I j k a k. This is the general definition of angular momenta. It doesn't tell you anything about what kind of angular momentum. It says this is what kind of properties they have. And so it suggests that if you looked at the formalism of angular momenta and did something, you would be able to derive general transformations of this form. That these coefficients ought to be tabulable because they don't care whether it's L and S and J or P, Q, and R. And so it should be possible to find such things. And they're called 3J coefficients. And there are various forms. They're called Clebsch-Gordan coefficients. They're called Wigner coefficients. No, they're not. They're called vector coupling coefficients. And, but the 3J is the one that most people prefer because they have some very convenient symmetry properties. So suppose we have 3 angular momenta, and so I'm going to switch to a general notation rather than L, S, and M, L, S, and J, and so we have an uncoupled basis, and we want J1, J2, J3, and we want minus M3 is defined as M1 plus M2. So this is a transformation coefficient, and we'd like to know what it is. And what it is this minus 1 to the J1 minus J2 minus M3, 2J3 plus a half, square root, times this magical thing, J1, J2, J3, M1, M2, and M3, I don't have room to write it here, so I'll just, M3 is minus M1 minus M2. So a 3J coefficient is 3 J's, 3 M's, ordinary large parentheses. These are tabulated. Okay, so if you one of the symmetry properties is if you make cyclic permutations. I'm doing this from memory because I can never, if you do cyclic permutations of the rows, then they're equal. If you do anti-cyclic columns, if you do anti-cyclic permutations of the columns, you have to multiply by a factor, and I'm pretty sure that factor is -1, the J1 plus J2 plus J3. I don't remember. So then there are other things. When do you know that these things are 0 and other factors? But there's a fantastic symmetry. These vector coupling coefficients, or the transformations you need, can be written in terms of these, which can be tabulated. And the tables can be small because there's so much symmetry among these things. So these are 3J coefficients. They're used always for going between a coupled and an uncoupled basis set. It's the most common thing you'll ever do in dealing with angular momenta. And so it's useful to practice with 3Js. Okay, but today we're going to talk about 6Js also, because the juxtaposition of the two is really quite wonderful. And if you accept 3Js, it's not a big step to go to accepting 6Js. Okay, so 3Js are used when you have 2 angular momenta coupling to make a third. If you have 3 angular momenta coupling to make a fourth, well then you can do it in 3 different ways. So suppose for hyperfinite atoms or for Rydberg states, it's going to be easy to come up with more than 3 total angular momenta. And so let's look at hyperfine. For hyperfine, you have a nuclear spin I. So for a given isotopomer, you know the nuclear spin. You find it in many tables. I prefer to use the little table in Townsend Shallow because it just has everything you need, and it has many other good things too. And then you want the total angular momentum. And that's always called F when you have nuclear spin. If you don't have nuclear spin, it's called J. And so you can get F by coupling J with I. That's one path. So J is L plus S for atoms. And another path would be, let's define G as S plus I. In other words, we're going to couple the 2 spins together, and then F would be equal to G plus L. So, and there is a third path. You could couple the nuclear spin to L. Nobody ever does that, because these 2 are the 2 possible cases that you might encounter. And so we have different intermediate angular momenta. We have J and G and something else that will go unmentioned. And so we might want to transform between 2 basis sets where we have the same values of L, S, I, and F, but different intermediate angular momenta, J or G. So we'd like to be able to transform between these 2 basis sets. So they're all massively coupled basis sets. The only thing that has a projection quantum number is F. And so how would you do this? Well, there's the easy way and the hard way. But since you don't know about 6Js yet, I'm going to tell you about the hard way. And then you will really like the easy way because 6Js enable you to do this. But okay, but why would you care? I mean, suppose we discover that there's a term in the hyperfine Hamiltonian that involves the dot product of I with S. And so if we define G as I plus S, well then G squared is equal to I squared plus S squared plus 2I dot S. And so if we want to know I dot S, we just replace it by G squared minus I squared minus S squared. And so we're going to clearly want a basis set that expresses explicitly G, I, and S. Well, that's too damn bad because most atoms also have spin orbit, which are L dot S. And that would not be compatible with the basis set that would be natural for this. And so you have to make it a Sophie's choice. Which one are you going to do a lot of work on? And usually you use the basis set where this one is diagonal because spin orbit is always big. And spin orbit defines the general pattern. But if L is 0, there's no spin orbit. So you do this. And so for all S states, the hyperfine, for all states where L is 0, in other words, S states, the hyperfine will be defined by this operator. And so, you know, in this, you're going to use that particular coupled basis. Often you'd like to think, well, why make a big deal about it? Why not just, you know, take what's given to you on a silver platter and use the nice basis set for it, and then do something that makes it possible to evaluate the other thing without doing a lot of work, using some kind of basis set transformation. Okay, how much time do I have? I really want to talk about Rydberg states, but I think I'd better not. So basically, I'm looking for cases where there are a lot of angular momenta. And maybe I'll talk about the Rydberg states after I turn the crank a little bit. I mean, whenever you have to couple 3 angular momenta to make a fourth, you're going to have this choice of which intermediate angular momentum are you going to use. And so you can do it the hard way using 3J coefficients. But what you have to do, it's really awful. Because, I mean, suppose now I'm going to talk in terms of this formal rather than explicit picture. So we have J1, J2, J3, J12, J, MJ. So that's one of the possible coupled basis sets. And suppose we want to go from this to one which is expressed in terms of J13. What do we do? Well, the first thing you do is you uncouple J3 from J12. You always start with the total angular momentum, the biggest one, and you uncouple the secondary thing from it. And that's the same thing as killing J. Okay, and so you have J1, J2, J3. And now you've uncoupled J3 from J12. So we have J12, M12, and M12 is, so you see we got rid of J and replaced it by M12. Now M12 is given by this conservation, so it's M J. Oh, I forgot. Okay, so we uncoupled J3 from J12. So here we have an uncoupled J3, and here we have an uncoupled J12. We've lost big J, and we still have M sub J, but as a constraint. But the M12 plus M3 is MJ, and so we did one step. Now we have to do another step, because in order to get from J12 to J13, for example, you have to completely uncouple and then recouple. So now we have to, what do we got left? Well, we still have J12. We have to kill it. And so we uncouple J1 from J12, or uncouple J1 from J2. And so now we have J1, M1, J2, M2, J3, M3. There's constraints, but I'm just not going to write them in. So we've fully uncoupled. And then we recouple. We want to form, we had a J12. We want to form J13. So form J13. So we have to couple J1 with J3. And so we get J1, J2, M2, J3. So when we couple to make J13, we lose M1 and we lose M3, and we get J13, M13. And then the last step is we recouple J13 and J2 to make J. And so each of these steps involves a 3J coefficient and a sum. You can do it. You know, it's not a big deal. You can tell your computer to do it. You don't have to do it on a piece of paper anymore. You can, you know, all of this stuff, all the 3Js are in the computer, and you just write this thing correctly. But the more steps, the more chance of an error, especially if you're scatterbrained like me. So it turns out there is a shortcut, and that shortcut is called 6J coefficients. And you can imagine, once you get the idea of 6J, that there are going to be 9J and 12J too. But we're not going to talk about them. So 6Js are created for the express purpose of recoupling, going directly from the this basis to the end point. So what you, if you want to go directly from a So suppose we have J1, J2, J3, J12, J, MJ. And you want to go to J1, J2, J3, J13, J, MJ. You could do this by these 4 steps, or you could simply say that the transformation coefficients between the 2 basis sets, J1, J2, J3, J12, Jm. This thing, the thing you want, if you wrote this out in the form of a completeness expression, then the coefficient you would want is this. And that coefficient has the value -1 to the J1 plus J2 plus J3 plus J. All of the things that are being conserved times the square root of 2J12 plus 1 times 2J13 plus 1 square root. The 2 things that are being exchanged. And then we have the 6J, which is J1, J2, J3, J. The 4 things that are being preserved. J12, J13. The 2 things that are being switched. You know, it's hard to hold 6 things in mind at once and to manipulate the symbols. But if you just realize it, 1, 2, 3, 4. These are the things. These 3 things are coupled to make that, and all of these are conserved. And the whole purpose is to exchange J12 for J13. Well, that's it. So these things are tabulated. And so you could use 4 uncoupling to recoupling steps and use a transformation that involves 4 sums over products of 4 3Js. Writing a computer program, that's trivial. However, you can write it as a simple 6J.
So what is the physical meaning of the very first part, the -1 to the sum of J's?
Yes.
Is there some meaning whether the sum of the J's is even or odd?
Yeah, well, if the sum of all of these things is
if it's even, you get them.
Okay, I mean, in order to get from this thing, which is not symmetric, to this thing, which has a lot of symmetry, you have to take out some factors. So that's all this is for. This is to be able to construct the most compact and symmetric table.
Okay. I see that. I guess I just don't understand what could possibly the sum of the individual J components and J, whether it's even or odd, what could that mean?
If I just suppose all the angular momenta are integers.
Okay.
I think you can probably show that this thing is always going to be even. Maybe not. You know, if one of them is half integer, then big J is half integer. And so you've got a combination of 2 things. I just don't know for sure. It's just, I don't think it has any particular physical significance. It's just a way of getting to an object which has fantastic symmetry properties. Now, here I have to admit that I am at a loss because in Edmonds, which is the standard source of wisdom about angular momentum, it tells me something which I don't understand. The symmetry properties. You can make symmetric or antisymmetric permutations of columns. No change. Well, how many of them are there? There are 6. You can take the top and bottom members of a given column, and you can flip 2 at a time. According to Edmonds, there's 4 of them. 4 ways you can do that, but I can only count 3. There are supposedly 24 permutations that give the same value. I can get 18. So there's something that I don't understand, and I haven't checked Edmonds against Brink and Satchler or any of the other standard sources. I suspect the number 24 is right, and he tells you to use a regular tetrahedron in order to figure out how many permutations there are. And the number of symmetry operations in the TD group is 24. But some of them don't seem to be appropriate for anyway, so that's a little thing. Okay, so I don't have time to talk about Rydberg states because I really want to talk about the Wigner-Eckart theorem. So it's really great. You can do the 2 sorts of things that you're going to want to do. I'll get to you in a second. You can uncouple using 3Js, or you can recouple using 6Js. Yes?
This notation of 6 things down here,
yes.
Does that represent a different function from the one up there?
Well, this, you mean up here?
Yeah.
This is a 3J, and it has both magnitudes and projections.
Well, yeah, but if I wanted to know what is the value of that thing, then there's some function for deriving it.
That's correct.
Is that the same as the one down there?
Definitely not.
Okay.
It's a completely different procedure.
So one of them is denoted by curly brackets and one of them is denoted
That's
by...
right.
Okay.
And when you get to 9Js, you have 3 rows of 3 and curly brackets. Okay, so now we want to, well, what is this good for? Well, it's good for evaluating matrix elements. I mean, you have a basis set. You don't want to admire the basis set. You want to use it to do something. And the thing you want to do is always evaluate matrix elements of the operators you're going to encounter.